This weird substance looks like it's from another planet, but it's actually called a ferrofluid. But what is a ferrofluid? A ferrofluid is a colloidal suspension of ferromagnetic nanoparticles in a carrier fluid in some kind of solvent. Ferromagnetic particles are particles in which the magnetic moments of the particles have a tendency to align, like iron, for example. But how is it possible that the particles don't just sink to the bottom, like you would expect for a metal? The nanoparticles are subject to Brownian motion, which randomly disperses the particles throughout the carrier fluid. Because of random collision and thermal excitations, a particle is in a random position at any time t. The dependency on the position and the time is given by r squared is 6 dt, with t the diffusion coefficient. This thermal motion overcomes the tendency for these particles to align and therefore to attract. For this not to happen, it is important for the particles to be very small, about 10 nanometers. This is because the diffusion coefficient is inversely dependent on the radius of the particles. In this case, the thermal energy is way bigger than the energy the particles get from aligning. There is, however, another problem with these kind of fluids. The particles have a tendency to attract due to van der Waals interactions, which does play an important role at these scales. This is solved by a coating of surfactant around the nanoparticles. When the particles get too close, there is an osmotic pressure created by the polymers which repels the particles. This is how the particles can stay randomly dispersed and we get these nice effects. Can we comprehend the pretty spikes? For that we need to take a look at 3 different effects. At first, the gravity influences the fluid. As the fluid is pulled towards the Earth, the potential energy decreases. Nature tends to decrease potential energy as much as possible. If there was only gravity, the fluid spreads itself totally flat. However, the second phenomenon causes the droplet to form more of a bubble. It is the surface tension. In fluids, for example water, the particles attract each other. That is because also in this case it is energetically favorable due to bonds. The more neighbors each particle has, the lower the total energy becomes. A fluid has the least surface and therefore the most neighbors when it forms itself to a ball. But what makes the ferrofluid that special are the nanoparticles. Nothing special happens under normal conditions, but when we turn on a magnetic field, the nanoparticles become little magnets themselves and are trying to chain together. The magnetism itself would result in high, small and sharp peaks. When we take the 3 compounds together, we found our ferrofluid behavior. The potential energy from the gravity plus the energy from the bonding plus the magnetic energy must be minimized to compromise to the ferrofluid behavior. Remarkable is that when the magnetic field is again removed, the fluid acts as a regular fluid again. Even with ferromagnetic particles, the fluid acts like a paramagnetic material. Random thermal motion prevents the fluid to stay magnetic as a ferromagnet. The random motion causes the magnetized fluid to quickly become unmagnetized. Apart from these very cool properties, ferrofluids actually have multiple applications in real life. Being designed by NASA in 1963 to design rocket fuel to the engines of a spaceship in the absence of gravity, ferrofluids are nowadays used in several different areas. Ferrofluids are for instance used to seal spinning drive shafts in hard disk, to remove heat from the voice coil of loudspeakers, and have promising prospects for various medical applications, such as enhancing contrast in MRI or magnetic hyperthermia.